Okay, welcome to electrical machine lecture. Uh, Today we are going to discuss the losses and power stages in the DC generator. So for that purpose, we are taking a DC compound generator. DC compound generator. We have taken the DC compound generator. The reason is that we want to introduce the series field winding and shunt field winding. So this is mechanically coupled with the prime mover. So this is nothing but the mechanical input. Finally, the output is the electrical output. So it is electrical output in the form of electrical energy. So output power, say PL, is equal to terminal voltage VT and load current IL. V into I is the power. So this much is the watt. Whereas mechanical input is either it is going to run by diesel generator, so it is a BHP or say whatever it may be the mechanical energy. So it is again, it is in the watt or British horsepower. So this winding, the generator having shunt field winding RSH. The current flowing in the shunt field winding is ISH. The generator induce EMF, it is EG, and it delivers the current IA, armature current. The series field resistance RSE, shunt field resistance is higher because it is connected in parallel with the armature EMF, whereas series field resistance and armature resistance is small. It may be a 0.1 or less than 0.1 ohm. There is two brushes contact drop also there, and this is the load current IL, which is going to flow in the external circuit. Okay, so it means that the input is mechanical. There is some magnetic coupling which we have already discussed, and the conversions are there, and because of conversion some losses are going to take place in the field winding, armature winding, and series field winding. At the same time, when the generator armature is moving at some particular constant speed, there is some windage and frictional loss also. Because of the friction, bearing friction, the friction loss, which converts into the heat. So that is called as a friction loss, and windage loss. We are providing some fan on the same shaft, so windage losses are there. Now, this windage and frictional loss, which is depend upon the speed, whereas the current in the armature and current in the series field winding is the function of loop. It means that if you increase the load current increases, whereas the shunt field current remain constant, so it will deliver more current. So whatever the losses which is going to take place in the armature and series field winding is the function of load. One thing. Second is that when armature is moving under the influence of magnetic field, say this is the one electromagnet which we have considered. This is North Pole. It is because of the field winding. Yes, so it will produces the constant magnetic flux. And say this is the North-South pole is there, but the same electromagnetic field or with the help of some current. So this is the South pole. Now it produces the constant magnetic flux. When armature core, which is made up of magnetic material, it is running or it is moving under the influence of magnetic flux or under the presence of magnetic flux. This is metallic part, that is it is a conducting part. So whenever the conductor cuts the magnetic flux, it induces EMF. So this armature structure, so if you look at as a three-dimensional view, so this will be this one. So it induces some EMF, but it does not find any external circuit as similar to the armature conductor, though. So there are different armature conductor over the periphery or slots are there. So this structure does not has any external circuit. So current is going to move or current is going to flow in the form of eddies, or it will circulate, and this current is called as a eddy current. Eddy current. Now this eddy current, say IE is the eddy current, and the resistance of material, so square of the current multiplied by the magnetic material resistance, then it will give the losses, isn't it? So this is called as a eddy current loss. To avoid or to reduce this eddy current loss, instead of using a solid material, solid, say circular, say shape of the core, we are using number of strips, or in the form of some disc, number of discs, they are nut bolted on the both side, and in between there is a varnish or say insulating material. So this type of structure is called as a laminated core. Laminated core. And because of this laminated core, the eddy current resistance is going to increase, and hence the losses are going to reduce. So it will reduce the current over the surface of material and so on. So this eddy current is used by fine laminations. If you are using, say, 1 mm, if you are using 1 mm thickness of the disc or the say lamination, the losses will be more. If you are using 0.5, if you are using 0.35 and so on, so the eddy current loss is going to reduce. So this is one loss which is going to occur in the armature structure, because it is a magnetic material. And second type of magnetic losses is called as a hysteresis loss. The hysteresis loss is depend upon the type of ferromagnetic material. If it is a soft, the losses will be less, isn't it? And the ferromagnetic material is used for the quick reversal of the magnetic flux, and hence there is some hysteresis loss. So hysteresis loss is going to reduce only by proper selection of material, whereas the eddy current loss is going to reduce only by fine lamination. So these are the two magnetic losses are there. So where is the losses? Losses is going to take place in the field winding. Now what is the field winding? The current ISH square multiplied by RSH is the loss. It is the loss of power in the field winding. Similarly, the loss of power which is going to take place in the series field winding. So ISE, if you represent the series field current, because in case of the short shunt, this will be outside this place, isn't it? So ISE. Similarly, the losses is going to take place in the armature. So it is a IA square RA. Say brush losses are there. Say brush voltage drop is VB multiplied by the current which is flowing inside through the brushes is IB. So this is the losses. These are the loss, power loss. It is the power loss. This is also the power loss. This also the power loss. So these are the losses which occurs inside the DC generator when converting from mechanical energy to the electrical energy. So one more losses are there here, and this is called as a windage and frictional loss. So windage and frictional loss also there. So these are the different type of losses are going to occur inside the armature, inside the DC generator. Now, if the speed of DC, if the speed of prime mover, if say speed of the prime mover is kept as a 1500 RPM, So you can say that the whatever the losses which is going to occur, irrespective of the load condition, the windage and frictional losses are constant because these losses are depend upon the speed of generator, speed of the prime mover. Now look at this field circuit. Whatever the load, either the generator is loaded or it is a open circuit over this one, but the shunt field winding carries the same current. So the shunt field current is again irrespective of the load circuit or load current, and hence the losses which is going to occur in the shunt field winding is also remain constant irrespective of the load condition. Whereas the losses which is going to occur in the series field winding, in the armature winding, in the brushes is the function of armature current or is the function of series field current and ultimately depend upon the load. If the load is zero, the losses occurs in the armature circuit and series circuit is almost zero. Whereas if the load current increases, the current in the armature, it is deliver more current and hence the more losses are going to take place. Therefore, the armature copper loss and series field copper loss are called as a variable loss. Copper loss, it does not mean the copper is going to reduce. It is the loss of power, and that loss of power is going to increase the temperature of motor. So this is the some classification of the DC generator or DC motor. Both the machine construction is same. Only the difference is that in case of DC generator, the input is mechanical, and in case of DC motor, the input is the electrical. So we will consider here as a DC generator, the same phenomena is going to occur in the DC motor when we are going to read or when we are going to learn the DC motor. So there are major three type of losses. One is the electrical loss. Electrical loss, the loss which is going to occur in the copper windings. It may be armature winding, series field winding, shunt field windings, and brush drop. So these are the losses. Okay. Now second group is the magnetic loss. The magnetic coupling is there, and because of this magnetic effect, the armature induces some EMF. It induces EMF, it circulates the current, and there's again losses are there. So it is called as a iron loss and the core losses because the structure is called as a core. It may be a field core is there, armature core is there. So it is called as a iron and core losses are there. And third is the mechanical or rotational losses are there. So in case of the DC machine, three major. One is the electrical loss, second is the magnetic loss, and third is the mechanical loss. So in case of the say electrical loss, in electrical loss, armature copper loss. So armature copper loss is nothing but current in the armature circuit, square of this current multiplied by the armature resistance. So it is in watt. So this is the power. This is the power loss in the armature circuit. Similarly, in case of the shunt field winding, the current is going to flow in the shunt field winding. So ISH, square of this current multiplied by the resistance, it is RSH. And similar series field current, so ISE, or it may be IA in case of both are connected in series, so RSE. So these are the losses take place in the armature circuit. Now out of these two, this one and this one is the variable loss because it depends upon the load condition for the DC shunt generator or DC compound generator. Whereas the shunt field current will remain constant, so it may treat as a constant losses. Now the second type of classification, that is the magnetic losses. That magnetic losses has two types. One is the hysteresis loss and second is the eddy current loss. The hysteresis loss depend upon the type of material, isn't it? And the quality of material. It is expressed as WH, hysteresis loss, which is equal to some constant flux density maximum flux density in the core raised to 1.6 multiplied by the F, that is the frequency, and V is the volume. V is the volume. So higher the frequency, the eddy current losses will be more, and it is depend upon the maximum flux density. If the machine is designed at a higher flux density, the losses will be more. And again, it depends upon the volume. More the magnetic material volume, more will be the losses. Second is the hysteresis loss. We may express as WE, which is equal to some constant K, maximum flux density raised to 2, frequency square, and thickness raised to 2 or thickness square, and volume. This much is the. Now see, if you are using 1 mm as a thickness, the square of 1 mm is 1. Whereas if you are using the thickness of the material or thickness of the lamination is 0.5, the square of 0.5 is 0.065. So it is means multiplication of this smaller number, it's go on decreasing. So if we are using thin material or the thickness of the lamination is a small, lamination thickness of the laminated plate is a small, high, then the losses is going to reduce. So this is called as a eddy current loss and hysteresis loss, and totally it is called as a magnetic losses. Whereas the frictional loss is going to occur in the bearing and windage losses because the moving part is under the air pressure and the air cutting is there, and if you are also providing some fans, so these are the frictional and windage losses are there. So these are the different losses in the DC generator. Now, in case of DC machine, we may call as a variable loss. Variable loss. Variable loss is the loss which depends upon or which is the function of load. So it is variable loss is the function of load. Means it varies with respect to the load condition. So armature current IA square RA plus ISE square RSE plus brush loss are the variable loss. Whereas the shunt field loss is the constant loss, or it does not depend upon the load condition. Now there is a stray losses. Stray loss, generally it is called as a mechanical loss. Mechanical loss plus magnetic loss. Magnetic loss are called as a stray losses. So addition of the magnetic loss and mechanical loss, windage and frictional loss are called as a stray losses. And whereas the constant loss which is constant irrespective of the load condition. So if you add in case of DC shunt generator as a shunt field winding, so it become a constant loss. So based on these losses, the power stages in the DC generator is as it is. So it is a mechanical input. Mechanical input is from the any type of engine whose capacity is given in bhp, 30 bhp, 20 bhp, and if you multiply by 746, so it become in watt. So there is a iron frictional losses are there. So iron frictional windage losses are there. So these are the stray losses. Now, after subtracting, if you subtract this value from the given input, we will get the total electrical power developed or gross electrical power developed which is equal to the EMF generated multiplied by the armature current. Actual EMF induced in the armature multiplied by the armature current is the gross electrical power done. But once it is generator is going to deliver the current, generator is going to deliver the current is going to flow from the armature winding, from the field winding. So some power loss is going to occur in this 2 or 3 parameters, and hence we have to consider the copper losses. So if you subtract whatever the power developed in the DC generator, the copper losses is subtracted, then we will get the total electrical output, or this is the useful output, and vice versa. If you have an electrical output, suppose the generator, it is delivering 5 kilowatt, means the output is the 5 kilowatt. If you add the copper losses, if you go from opposite side, so you just add these losses, what happened? You will get the gross electrical power. And if you add the stray losses or constant losses in the gross electrical power, we will get the electrical input, or we will get the generator input. So by this way, it is possible, if you just remember this power stages, mechanical input, some iron windage and frictional iron losses are there, then it will develop the gross electrical power. From this gross electrical power, if you subtract the copper losses in the 3 windings or 2 windings, then we will get the electrical output. So this is called as a power stages in the DC generator. So from this power stages, we can say that the electrical efficiency, which is equal to power available, or the useful power V into I divided by total power or electrical power generated, which is nothing but the EMF induced multiplied by the armature current multiplied by some efficiency. It's 100, so it is a percentage efficiency. But it is used only for the design purpose. What is the losses? How much is the losses are there? Whereas we are considering the overall efficiency, or it is called as a commercial efficiency. Overall or commercial efficiency. Generally, whenever the efficiency is there, it is the commercial efficiency. Commercial efficiency, which is equal to the useful power, that is the power available in the external circuit, divided by generator input, is the generator input, that is the mechanical power. So whenever some questions are asked, calculate the efficiency, the meaning is that it is a commercial efficiency. It's nothing else. Okay. So now, if you want to write the total losses, so what is the total losses? The total losses are the armature copper loss, IARA, plus series field copper loss, if it is given, ISE, RSE, plus shunt field copper loss, so it is ISH square, RSH, plus windage and frictional loss, or hysteresis loss. So this is the total losses are there. Now this shunt field copper loss and this one, it is called as a, say, it may be called as a constant losses. So we can calculate from this one. So this is the different power losses in the DC generator and power stages are there. Now we will see the condition for maximum efficiency. Condition for maximum efficiency. So under which condition the generator gives the maximum possible efficiency. So we will use same nomenclatures. So generator output, which is the useful output. So it is V into I, means the voltage generated or voltage at the terminals and current in the load circuit. So it is the V into I. Whereas generator input it is can be written as generator generator output plus losses, whatever the total losses are there in the generator. So generator input nothing but the generator output plus losses. Now we can write the generator output. The generator output is V into I, is the output of generator, plus losses. What are the different losses are there? One is the armature current loss plus constant loss. Constant loss, the loss, shunt field copper loss. We are using only the this is the let DC shunt generator. So we are using DC shunt generator. So there is a series field losses are not there, and the shunt field copper loss plus magnetic and mechanical losses are considered as a constant losses. So WC is the constant loss, which is equal to V into I plus I, we can write as a shunt armature current, which is the combination of load current plus shunt field current, bracket square RA plus WC. It is the constant loss. Okay. Now, in case of DC generator, say we will draw the DC shunt generator, so it become easy to remember. So this is DC generator whose terminal voltage is V. Current in the load circuit is I. Current delivered by the generator is IA. Current in the shunt field winding is ISH. This is RA. This is RSH. So we can say that I plus ISH. So IA is nothing but I plus ISH and this one. At full load or at load current I is very large than shunt field current. Shunt field current means if the load is 100 ampere, whereas the shunt field current is 2.5 ampere. So we will say neglect, and we say that the armature current IA is very nearer to the I. So under such condition, the efficiency is equal to output divided by input, which is equal to output is V into I, and input is output plus losses. So V into I is the output, IA square RA plus WC. Okay. Now it can be written as IA can be written as it equal to the load current. So V into I divided by V into I plus I square RA plus WC. So just because of the very armature current is very near to the load current. So now we can write above equation as 1 plus 1 plus I into RA upon V plus WC upon V into R in the second line. So what we have done, we have divided the numerator and denominator by V into I. So V into I is become 1. So it is become 1 I square RA divided by V. So 1 I get cancelled because of this square of this current. And WC is as it is divided by V into I. So for efficiency should be maximum. For efficiency maximum, what we need? We need this is equal to 0. Then the efficiency will be maximum. Or we can say that the denominator should be minimum. Or for maximum, when denominator is minimum. Okay. So it means that the derivative with respect to current, because the current is a variable one, which is depend upon the current, which is depend upon the load, d into di with respect to, means derivate the denominator with respect to I. So I into RA divided by V plus WC upon V into I, and keep it is equal to 0. So after doing the derivation, we get RA upon V minus WC upon V into I square is equal to 0, or you can write as I square RA, means if you just come here, so I square RA, VV get cancelled, is equal to WC. So this is the condition. If this condition satisfied, the generator will give the maximum efficiency. Means when copper losses become equal to constant losses generator gives maximum efficiency. So to obtain the maximum efficiency at a higher load condition, we must keep the constant losses minimum. Means we have to design the generator in such a way that the magnetic losses will be small, windage and frictional losses will be small, then it will give the a better maximum efficiency value. So under when the variable loss, or you can write variable, because this is the variable one. So when the variable loss become equal to the constant loss, the generator gives maximum efficiency. So under maximum efficiency, what would be the current? The load current, corresponds to maximum efficiency means C. So we can write as, so it is I square RA is equal to WC. Therefore, IA is equal to WC upon RA under. So this is the current under which the generator shows its maximum efficient current corresponds to maximum efficiency. So this is the some power stages in the DC generator. What are the different losses in the DC generator? It will remain same. In case of motor only, the sequence is going to change. The input is with the electrical and output will be the mechanical. Whereas the type of losses, the behavior of losses will remain same. So next time we'll do some numerical on the losses and efficiency to clear the same concept. Thank you.